Dear students, now I am going to prove root 8 is not a rational number. We know that root 8 equals to 2.828427125 and so on. By using the concept of real numbers and axioms, let us prove root 8 is not a rational number. Here we have to prove root 8 is not a rational number, but let us assume root 8 is a rational number on the other hand. If root 8 is a rational number, root 8 can be expressed in terms of p upon q, where p greater than 0, q greater than 0. We also assume q should not be equal to 0 because it is a rational number. For rational number, important condition, q has to be not equal to 0. Now p and q are selected such that their GCD of p and q must be equal to 1. That is, they have only one common factor, that is 1. They do not have any other common factor other than 1. That implies that we cannot cut p and q by some like 2 1s are 2 3s are. We cannot cut it. They are not cuttable. That is a last proportion of p upon q. They are in the already simplified ratio, and that ratio cannot be further simplified. Therefore, GCD of p and q taken as a 1. Let us call root 8 is equal to p upon q as a equation 1, and GCD of p q equals to, let us call it as a equation number 2. Since we know that root 8 greater than 2 and root 8 smaller than 3 implies root 8 is greater than 2 and less than 3. Let us call this equation as 3. Here I have written again equation 1 2 3. In equation 3, root 8 is there. The root 8 can be replaced by p upon q. So we get p upon q greater than 2 and less than 3. Let us call it as a equation number 4. Multiplying each term by q, I get 2q p upon q into q less than 3q. Q get cancelled here. 2q p and 3q. Subtracting 2q from each term, 2q minus 2q, p minus 2q, 3q minus 2q, 0, p minus 2q, and 3 minus 2 equals to 1q. Let us call it as a equation number 5. Here p minus 2q is positive number, positive real number, and p minus 2q less than q. Here equation 5, we are going to multiply each term by root 8, that is 0 multiplied by root 8 and root 8 p minus 2q less than root 8 into q. Here root 8 p minus 2q is not an integer because it got multiplied by root 8. Let us call it as a equation number 6. Now root 8 p minus 2q, root 8 is nothing but p upon q, and here is a p minus 2q. Now we are going to open the RHS. We get p square upon q minus p upon q into 2q. Now here q get cancelled, q get cancelled here, and here p square, here q, I am doing multiplying and dividing by q, minus p, and 2 got multiplied, therefore 2p. This can be written as p square upon q square multiplied by q minus 2p. P square upon q square, nothing but, since p upon q equals to root 8, therefore p square upon q square equals to 8. Here p square upon q square can be written as 8q minus 2p. 8q minus 2p is nothing but, it is an integer. It is an integer. Let us call it as equation number 7. Now we are having the two equations. One is a 6 number. In the 6 number we have stated that it is root 8 p minus 2q is not an integer, and in equation number 7 we are telling 8q minus 2p is an integer. So in state number 6 and in the statement number 7 we are telling exactly opposite statements. They are contradicting each other. Therefore we prove that root 8 is not a rational number. Now I am taking a next question, and that is prove that root 2 is not a rational number. Solution: root 2 is not a rational number. We will go for against the statement, opposite to the statement, and I say that let root 2 is a rational number. They wanted to prove not a rational number, but I am assuming let root 2 a rational number. If root 2 is a rational number, then root 2 can be expressed in terms of p upon q, where q not equal to 0, p greater than 0, and q greater than 0. These are the three conditions. If root 2 is a rational number, then root 2 equals to p upon q, q has to be greater than 0, and q has to be greater than 0, and q is not equal to 0. Also, one more important condition, that GCD of p and q equals to 1, that is p and q are two numbers such that there are no common factors is available other than 1 between them. Since root 2 equals to p upon q, squaring both sides, we get root 2 square equals to p square upon q square, implies 2 equals to p square upon q square. This can be written as p square upon q square equals to 2, implies on cross multiplication p square equals to 2q square. The RHS part is multiple of 2. RHS part is a multiple of 2. Therefore, we say that p square is a even number. If any number is a multiple of 2, that is equals to even number. Therefore, it implies p square is a even number. When p square is a even number, implies p is also an even number. In above case, we thought root 2 is a rational number, and the conclusion is p square is equal to 2q square and p equals to even. We got the two conclusions from above discussion. Now we will consider case number 2. Under this condition, we assume p equals to 2n minus 1 because even number minus 1 equals to odd number. So p equals to 2n minus 1, squaring both side, therefore p square equals to 2n minus 1 whole square equals to 4n square minus 4n plus 1. Here is a p square, so p square equals to 4n n minus 1 plus 1. Now 4n minus 1, this is nothing but even number because it is multiple of 2, therefore it is even number. But even number plus 1, this becomes an odd number. That implies p square equals to odd number, therefore p is equal to odd number. Let us call this as equation number 3, and we had already equation 1 and 2. In the equation 1 and 2, we spoken that p is an even number, and in the equation number 3, we are speaking that p is an odd number. On the one side we are telling p is an even number, and other side we are telling p is an odd number. That means both the statements of equation 1, 2 and 3, they are contradicting each other. Therefore we need to consider one more case. So let us case number 3. Under this case, let us consider p is again an even number. We start our statement, p is an even number. When p is an even number, I can go for p is equal to 2m. Let us assume it is an even number, therefore every even number is a multiple of 2, squaring both sides, p square is equal to 4m square. Okay, let us call it as a equation number 4. Till now we are having 4 equations. I have rewritten again here, and now from equation 1 and 4, LHS parts are same. So comparing RHS parts, we get 4m square equals to 2q square, 2 1s are 2 2s are cut down, q square equals to 2m square, implies q square is an even number because q square is nothing but 2m square, where 2 is an even number. Anything multiplied to even number is an even number. We have q square equals to 2m square. Q square is an even number, therefore implies q is an even number. If q is an even number, we can express in some suitable form because it is an even number. So let us write it as a 2n. N is any natural number. So I am just introducing a new letter n, where n is any natural number because q is already an even number. Therefore q equals to 2n. Let us call it as a equation number 6. And from equation number 4, I am already having p square equals to 4m square and implies p equals to 2m. So I am having now two outcomes. One is a P equals to 2m and Q equals to 2n. These are the two expressions I am having. Therefore, P upon Q equals to 2m upon 2n, and we already spoken that P and Q should not have any multiples. They should not have any multipliers if it is a rational number, but here we find that P and Q are having common factor, that is, a common factor is a 2, whereas earlier we spoken that they do not have the common factor. That means the result of this and what we thought in the case number 1, they are exactly opposite of each other. In the step number 1, we thought that the GCD of P and Q equals to 1, that is, they do not have any common factor, but at the end we are telling that P and Q are having the common factor. That means the above two statements are contradicting each other. Therefore, our statement of P equals to our statement of root 2 equals to a rational number is wrong. Hence, at the end we confirm that root 2 is not a rational number.